Finding the roots of any equation is an important part of any discipline that is math heavy. There are some algorithms to easily find the roots of equations. For example, the Sridhar-Acharya formula to find the root of the quadratic equation, as shown here. However, as an engineer, there are many equations we might have to solve which either do not have such an elegant analytical solution, or the analytical solution exists but it is too impractical. Fortunately, there exist numerical solutions which can help us come to a reasonable approximate answer. For example, the numerical solutions for roots of equations can be divided mainly into two broad categories: bracketing methods and open methods. Why we call them these will become apparent shortly. First, let's take a look at bracketing methods. One of the bracketing methods in particular, the method of false position, otherwise known as regular falsi. The method of false position, or regular falsi. What we have here is a function f of x. Suppose this curve represents the function f of x, and we'd like to find the root right here by some numerical method. First, we evaluate the value of the function at any 2 points, xl as in x lower and xu as in x upper. The 2 points should be such that if f of xl is negative, then f of xu is positive. That means we're looking for 2 points xl and xu such that if xl is over here, we get f of xl as a negative value, and if then xu must be here, f of xu must be a positive value. What the method of false position does is that it draws a straight line between these 2 points xl and xu. F of xu and f of xl. We draw a straight line between these 2 points. Now, we know the equation of a straight line joining 2 points xl and f of xl. These 2 points xl, f of xl, and the point xu, f of xu. These 2 points right here. The equation of the straight line joining these points is given by x minus xu divided by xu minus xl equals to f of x minus xu divided by f of xu minus f of xl. Now, if we plug in f of x equals to 0 for x equals to xr, we get xr minus xu divided by xu minus xl will be equal to 0 minus f of xu divided by f of xu minus f of xl. Alright, so what we're actually doing is we are plugging in this value into the equation of the straight line, this straight line joining f of xu and f of xl. Now if we solve this equation, we will get xr is equal to xu minus f of xu times xl minus xu divided by f of xl minus f of xu. And this is the equation that we'll need to solve our problems. This value xr is where the straight line evaluates to 0. That is, if we look at the graph we drew before, which looks something like this, with xu here, f of xu here, and xl here, and f of xl here. This is the joining line. Then the xr we got is over here from this equation over here. This equation gives us this xr value, which gives f of x. What we'll do next is f of xr, and we are going to replace xl or xu over here. We are going to either replace xl or xu with xr depending on xu and f of xr has the same sign, or if f of xl and f of xr has the same sign. That is to say, if f of xr is positive and f of xu is positive, then we shall replace xu with xr. This will become clearer if we go to a problem. Suppose we have this function f of x is equal to minus 25 plus 82x minus 90x squared plus 44x cubed minus 8x to the 4 minus 0.7 x to the 5th. So, and we are given the initial guess as xu is equal to 1 and xl is equals to 0.5. First, what we're going to do is draw this chart. And then xl, and then xr, and then f of xu, and then f of xl, then f of xu, then xr, then f of xr. So now what we're going to do is, first iteration, we have xl is equals to 0.5 and xu is equals to 1. So f of xl will be 1 point, and we're going to use a calculator for this, obviously. 1.52, and f of xu 2.25. Then we plug the values of xu, f of xl, and f of xu this equation over here to get the value of xr. And the value of xr, if we calculate it from that equation, will be 0.7019. Now what we'll do is we'll plug in this value into this equation to get f of xr, which evaluates to 1.3703. Now as you can see, this positive value, and this also evaluated to a positive over here with the value of xr we obtained in the next iteration. So in the second iteration, xl remains as is, but xu is changed from 1 to 0.7019, and so f of xl is still minus 1.52, but f of xr is now 1.3703. Now if we calculate xr again, we'll get 0.606. Now we could go on and calculate f of xr again, and then we could do a third iteration. If this time it were for some sake, say a negative value, then we'd have to replace xl over here because f of xl is negative. xl over here would have to be replaced, but if it was still a positive value, then we'd have to replace xu again, and we'd continue with this iteration until we were satisfied that we got an accurate enough value. Now if we look at this graphically, what's really happening is that this is f of x, and this is the root that we are actually looking for. This, by doing this, we're choosing a lower limit and an upper limit which bounds the root like so, and we draw a straight line because we don't know what the function exactly looks like, or it would be too difficult to do it in real time. So we assume this is a straight line between them, and then we find where the straight line intersects the x-axis, and that is our xr value. And then what we do is we take this value and we draw a second straight line over here, and then we calculate this value. This is our next xr. So we keep doing this until we are close enough to the root that it serves whatever purpose we are looking for. The final thing I would like to touch on is that why this is called an bracketing method instead of an open method. As we saw, the bracketing method here, called the bracketing method because the upper limit and the lower limit we chose bound the root in between them, as in it is bracketed in between the upper and lower limits. A very similar method to the regular falsy or method of false position is the second method, which is mechanically very similar because it starts with two initial points just like this, but in this case, in case of the second method, this is regular falsy and this is secant. In case of the second method, the initial guesses are on one side of the root, as opposed to the initial guesses in case of regular falsy being on either side of the root. So that's why this is called a bracketing method, and this is called an open method. So that's it. That's my tutorial on the roots of equations by numerical methods. And my name is Naqib Mashrur, and I made this tutorial specifically to apply for the position of lecturer at Daffodil University on the 14th of July. That's about it. Thanks a lot.